Okay? The way we're learning today is through geometry. If it's a nice shape, we can use geometry. Because integration is the area underneath the curve, right? And we can find areas of like rectangles and simple shapes. And then the last one is antiderivatives. Which is reversing the derivative. So if I tell you that f prime is, if f prime is 2x, what could f be? X squared plus a constant, c. So we talked about that briefly a while ago. Okay, here's the test. Is it going to, oh, it's not going to do it. Okay. So when we do integration notation, which integration is another form of antiderivative. It's just another vocabulary word. This is what it looks like. We have a kind of a capital sigma. It looks like a little bit of an S. There are bounds, a lower bound and an upper bound, a to b. Then you have your function. Now there's a difference between lowercase f's and capital F's. This is a lowercase f. Once you integrate, it equals capital F. Okay, so make sure you're very specific if you're using a capital or lowercase. Okay, and so A is your beginning bound, B is your ending bound. This is called a definite integral because there's a beginning and an ending point at which you're finding the area. Later on we go to infinities and it's indefinite because it goes on forever. And we have our height, f of x, isn't the y-axis the f of x as you plug in, and d of x is the width. Okay, so to the right, is it on the right side or is it down below? Our example looks like it's down below. Example 1, we're going to evaluate the integral of the function 4 from 2 to 5. What does the function 4 look like? Straight line. Got 1, 2, 3, 4. But we're going to only evaluate it from 2, 3, 4 to 5. So we're looking in this section, the area there. So this is f of x, no, this is lowercase, equals 4. What's the width? Because the width is dx. What's the width? The width is 3. And our height, in this case, is 4. This is a nice one to just use geometry. So if we integrated that, we would just do length times width and get 3 times 4. So area equals length times width. 3 times 4, so you'd say the area underneath the line from 2 to 5 is 12, right? In integral notation, that would look like this. Practice drawing those integral signs. From 2 to 5, if we integrate 4 dx from 2 to 5, we get 12. The same thing. Okay. I think on the right side I skipped that one. Is that the same thing? Mine's different than you guys' is. Determine the area created by the graph. We already did that while doing example 1. Okay, quick review of an area of a trapezoid. Does anyone remember the area formula for a trapezoid? I'll draw one. And just a sec after I put this up a little bit. Okay. A trapezoid looks like this. Two sides are parallel, the other two are not. And it's a quadrilateral, or four sides. They could also look like this. Two sides are parallel, the other two are not.
I'm going to do a square and a triangle.
Do you guys know it?
It's like writing under the formula.
Well, it says use it because it was made for a smart software, well, a different software than smart, and it was hidden there, so you could just erase it. But this is a PDF, so I can't just erase it, so it will be shown. So we have to handwrite it. Okay. Well, you're right. There is a square, maybe a rectangle, and a triangle. But this way, there's a rectangle and two triangles. Isn't a triangle's formula 1/2 base times height? But we actually have two different bases. And if I divide it there, I have two different triangles. That triangle has a different base than the blue triangle above it. So the formula is 1/2 base 1 plus base 2 times height. Because there are two different bases, depending on which triangle you're looking at. Okay, so it's there. It's just really, really light and really small. Okay, example 2. We're going to integrate 3x dx from 2 to 6. So first, we have to know what 3x looks like. What type of function is 3x? Linear. And this is 3x plus 0, so the y-intercept is 0. You go up 3 and over 1. Looks like we're counting by 5. So 1, 2, 3, 4. Up 3, over 1. You go up another 3, over 1. Up another 3, 6, 7, 8, 9, over 1. And continue that on. It'll look like that. But we're only integrating on the interval 2 to 6. 2 to 6. If I plugged in 6, what would my height be? So I can find this exact point. If I plug in 6, it'd be 18. Okay? So we're integrating so that we can find the area under, we say under the curve, in this case it's straight, under the line, and it happens to be what shape? A trapezoid, because we have two parallel sides, the left and the right are parallel. So you can just use geometry. The area of a trapezoid equals 1/2. Now the bases are the parallel sides, so be careful, because this time the base isn't actually on the bottom. How long is this first base, which is this side length? Because the bases have to be parallel. It's not 2, actually, it's 6. Because if you plug in 2, 3 times 2 is 6. Plus, how long is this base? I know it's weird because it's on the side. 18. Now the height, bases and height are always perpendicular. So is this red line perpendicular to our green bases? No, so this is not the height. That's called a slant. The black line from 2 to 6 on the x-axis, that is the height because it's perpendicular. And how long is it from 2 to 6? 4. Okay, so let's see, 6 plus 18, 24 divided by 2, we get 12 times 4, so 48. So I would say the antiderivative, or if we integrate from 2 to 6 of the function 3x dx, we get 48. Okay, would you go to example 3 and try that one by yourselves, please? Alrighty, Reed, would you go up to the board and show what you have, please? Thank you. What do you guys think? Did you get the same? Yeah.
No, when we do the integral, we don't need to put like unit squared or anything, right?
Unless it was a story problem. On a story problem, I would do that. Okay, just for notation's sake, to show equivalent statements, I would add in, continuing down your thought of equals, to show this is equivalent to this, which is equivalent to this, which is equivalent to this. And then I would just put an arrow. That's where my next step went. And then box. Because what will be graded, and some of you guys, actually many of you didn't do this on your let's see, you didn't box anything. Okay, you have to box what your final answer is. And if you at some point you cross something out, that will be skipped completely. So don't cross out something that's valuable, that's worth points. But good. Okay, and another thing I was going to mention, he did this perfectly. You have to have these parentheses because this is your height times your width. And that whole binomial need a t. That whole binomial is being times to the width, so you have to have the whole function in parentheses, because dx is your width. Okay? Really quickly, number 4, y equals -2, that's just a horizontal line, right? This is little f at -2. If we do 1 to 5, looking at this area, it's a rectangle, so area equals length times width. Okay, but be careful. What is the length of this? What's the length? The width is 4. Okay. Normally we'd say length can only be positive, but when we're doing integration, it's the signed area. So the length is -2. So we get -8. So that integral from 1 to 5 equals -8. Okay. Over to the right side. What type of function is x squared plus y squared equals 25? It's a what? Circle. Is a circle actually even a function? Because I just called it a function. No, it's not. Can I erase this? I see people still writing. Would you solve our circle here with radius 5 for y? Because it has to be a function in order to integrate. Would you solve this for y? And then it will be a function. Oops. Yeah, solve for y. Okay, so you should have y squared equals 25 minus x squared, or y equals plus or minus square root of all of that, 25 minus x squared. So this becomes a square root function. Let's see. Your example is not here. Okay, so we're going to integrate the square root function from 0 to 5. Square root of 25 minus x squared dx. And the x should match your variable. If for some reason this variable is like r, we'd put dr. Okay? Sometimes you also see delta x. What does this function actually look like? Now that we've solved it for y, it's a square root function. The positive square root looks like what? Do you think it'll be like this? What do we get when we plug in 0? When you plug in 0, yeah, because remember the circle with radius, this is the circle centered at 0 with radius 5. So for our purposes, we only look at the positive, so it'll just be the top half, where this is 5, this is -5, and this is 5. And we're just integrating from 0 to 5, which is right here. Actually, we're doing this in 10th grade honors right here. Here's circles. If there was a shift, if it wasn't centered on the origin, the x's and the y's would have something added or subtracted to it. Okay? Now, what's the area of a circle? Formula for area of a circle.
Plug in 0 for x, so you got 5, but why are we only making the positive?
because otherwise it's not a function. If I put this down here, it's no longer a function.
So when we integrate, we only look at
The positive.
make it into a function.
Mm-hmm. Okay, what's the area of a circle? Pi r squared. Now in this case, we're not integrating for the entire circle. We're only integrating from 0 to 5 of the positive half. So what portion of a circle is this shaded? 1/4. So for our area, we're going to do 1/4 pi r squared. 1/4 pi times the radius squared, which ends up being 25/4 pi. If the directions don't say round the decimal, I would leave it like that, because that's the exact value. And so with your integrand, you put equals 25 pi over 4. And all of this, you need not just box the answer, but with the integral. Okay. The next one, we finally move into some fun stuff. Okay, flip it over to number 6. So now we have trig functions. Now with a circle, we know a formula of a nice round symmetrical half circle. The next one is a trig function. Where is it? Example 6. For right now, and once we get into a day or two, you'll know why this works. For right now, memorize this. If you integrate sine x from 0 to pi, it equals 2. For today's purposes, you need to memorize this. Okay, a sine graph, remember, looks like this. What are the critical points on the sine graph? What's right here? Pi, 2 pi, and then our maxes and mins are 3 pi halves and 1 pi half. Okay, so on part A, if we're integrating, and from 0 to pi, this is the one you're memorizing, that half of that equals 2. Okay, part A, we want the whole thing, though. Integrating sine x from 0 to 2 pi, the whole period. So we have this area, and we have that area. Yeah. Because from 0 to pi, that is 2, because it's positive. But what about this section? It is negative 2. So if we add them, we would get 0. So the area is 0. That's weird, because they cancel each other out. Okay, what does the absolute value of sine x look like? Everything has to be positive. Is this chunk positive? Is this chunk positive? No, so how would we make it positive? Flip it up, so it looks like 2 little bumps. Bump, bump. Okay, from 0 to 2 pi. Here's pi. Okay, Claudia, from 0 to pi, what's the area? 2. Okay, Hala, from pi to 2 pi, what's that area? 2. So in total, we would get 4. Okay, sine x from negative pi to positive pi. So here's negative pi to positive pi. Okay, Ethan, what would you get for the area? 0, because they cancel each other out again. Okay, now the last one is the function is 2 plus sine x. We know sine x looks like this, but it's a vertical shift up 2, so I'm going to put my, oh gosh, what do you call that, midline? Up there. Yep, my pretend x-axis. And then I'm going to draw a sine, and we know sine has, oops, I kind of missed that a little bit. Sine has a height of 1, or an amplitude of 1. So go up 1. I feel like I'm totally missing the spot. Here's the spot. I'm going to mark that so I can actually see it. There we go. There's 2 pi, here's pi, and here's 0. Okay, now we're talking about the area under the curve from 0 to pi. But that doesn't just mean here. It means all the way down. All that good stuff too. So we have 2 shapes. We have the little sine bump, and we have a rectangle. Yep, what's the area of that little sine bump that has still an amplitude of 1? That is 2. And then we just do length times width on this little rectangle. So we're going to have 2 plus the length times width of the rectangle. How tall is that? So shift it up to 2. So 2 times, how wide is it? Pi. Okay, so we get 2 plus 2 pi. So I would rewrite it so it's nice and pretty and work's not in the middle. Dx, these parentheses are important because all of that is the height. Those parentheses have to be there. Equals 2 plus 2 pi. Any questions on those trig functions?
So why do they use the bottom area instead of on the rest of it?
You go all the way to the x-axis. So all of these have been shaded no matter if they're above or below, up or down to the x-axis. Yeah?
These side ones like this, you always do the top.
As long as amplitude is 1, then you know that it's equal to 2. Is that what you're asking, that this little hump is 2? Okay. Okay, number 7. Let's have you try that. Number 7, you're going to integrate 1 minus absolute value x from -1 to 1. So I would draw it out first, and then try to decide what type of geometry rules or formulas could you use to get that. Number 7a. I think we're starting to at least get A done. Just a couple issues with graphing. This is a vertical shift, but it's negative absolute value x plus 1. So the vertex is shifted up 1, but the negative does what to the graph? Flips it. Then we have the slope 1 over 1, or negative 1 over 1. So then we just want from here to here, negative 1 to 1. Is that area positive or negative? It's above the x-axis, so it's positive. It's a triangle. So what's the area of a triangle? Yeah, you can do the two individual triangles, or you can use this as the height as long as height is perpendicular to the base. So we can say area equals 1/2 base times height. The base was 2, height is 1. So you get 1. So I would do the whole integral equals 1 and box it. Next one, same graph, but different bounds. This time we're going from negative 2 to positive 2. Oops, I guess we'll write those up there. And this is area up to the, or down to the x-axis. So we still have that. And then we'd also have, some of you have started doing this, and it looked like your shading was okay. So we have both positive area and we have negative area. So remember, you have to use signed area. We already know this guy on the top is 1. Area equals, we have 1 plus, and we have 2 of these base times heights again. Because are these triangles exactly the same size? So I can just say there's 2 of them. 2's cancel out, and their base and height is, ooh, careful. The base is 1, but the height is negative 1. Plus the base is 1 times height is negative 1, which makes, and see the equivalent equal signs? 0. And you can actually even just visualize that by looking at it, right? Because you can see these triangles match one of the positive ones, and they cancel each other out, and we get 0. Okay, the title for the next table ended up being at the bottom of this page. Table 6.2, rules of definite integrals. Give me a sec, some people are still writing. Okay. Anyone still need time? Okay, now because we don't know how to integrate using antiderivatives underneath the curve yet, we're given some information. Because does anyone know the geometry of that curve? This shaded shape? I sure don't. So unless you guys know more than, oh, I don't know. Okay, make it a little bigger. But they do tell us that the current function's area from 0 to 1 is 1/4. We're going to find, we're going to integrate x cubed plus 3 from 0 to 1. What's the only difference? There's a vertical shift. Up, 1, 2, 3. So our curve, there's our new fake x-axis. Our curve, let's see, that goes up 1. Looks something like that. But we want this area here, and we want this area here. So we have a rectangle, and then we have that kind of curved, almost a triangle wedge. In this case, the area There's just no room. Area is, we have a rectangle plus, what's the area of the red portion? 1/4, because this wedge is the same as the shaded one that they gave us was 1/4. Okay, Joanna, what's the length and the width of the rectangle portion? After we've shifted it up, it creates that rectangle. 3 and 2. Yep. So 3 times 2 plus the 1/4. So our area is what? 6 plus 1/4? So we'd say the integral of... Huh? What?
The integral is only going to 1.
Oh, 0 to 1. Okay. 0 to 1. So 3 and 1/4 plus 3 parentheses dx, that equals 3 and 1/4. Please, on your homework, every time rewrite the integral, or the integrand, I think it's called. Okay, do you guys have calculators? Pull them out. I'm going to show you this last one, how you can do it on your calculator. Now, the problem with using your calculator in an AP test is that your calculator notation is not an acceptable way to show your work. You can use your calculator to do integrals, but you must write the setup. You must write this integral notation or you don't get the credit. If your answer comes out of the blue and you have no proof that you know what you're doing, then you don't get the credit. You have to be writing this stuff. If you use your calculator to integrate, you have to do the setup, and you have to write it in integral notation.
But I don't need to show any work.
As long as your work, as long as it's the calculator portion of the test, your work is showing the setup, and then you plug it in your calculator. But if you don't do the setup, and you don't write the calculator's notation, because we'll show you what that means here in a sec. And some of you have the newer calculators, right? So yours is going to be slightly different than mine. Where is it? Okay. Using a graphing calculator, we're going to integrate our exponential function here, e to the negative x squared dx from 0 to 5. These are the steps on your calculator. Let me get here a camera, this one. Okay, turn it on, clear anything out. I have some weird stuff from the other class. Okay, go to math. We've kind of already done this before. We have derivative in there, right? You go down, there's your derivative. You can find the derivative and we can find the integral. So select number 9. And as your notes say, this is how you type it in. After the parentheses, you put in your function. We want to integrate with respect to x. Then you need your beginning bound and your ending bound and commas in between all of those. Okay, so this is our function. Well, you can actually see it right here. We're going to type in e to the negative x squared, comma, we're integrating with respect to x, comma, our beginning bound or lower bound is 0, and our upper bound is 5. Okay, so that's how I'm going to type it in. Second e to the, now the negative x squared needs parentheses, negative x squared, close the parentheses, so that's my function. Comma, integrating with respect to x, comma, lower bound was 0, comma, 5, and close the parentheses. And you have a fancy way. Can you hand me your fancy calculator? Oh, not so fancy, I'm sorry. Here, let me come around and make this easier. Okay, at least they're not like smartphones where they have glass screens. Okay. Okay, so we go to math. It's still number 9, I think. And then you just, look how pretty that is. You just push in the numbers 0 and 5, and then you type in your integral, what was it again? E to the parentheses negative x squared. Yep. And then see where it says D and then a box? That's your x. It even already does the alpha. So you put dx because you're integrating with respect to x. You have your function and you have your bounds.
So could you put another variable to type of x, like dx?
Your calculator only does x, but you could be integrating with respect to t or r, but when you do it in your calculator, you just always use x.
If you integrate for some t or r, would your function still have an x in it? Could it still?
No.
So
Well, it can if you do partial differential equations, but that's after Calc 3. So I'm not going to teach you partials.
I think my friend that's what she.
So I put enter, I get this, and I put enter on my calculator. They're the same. Yes, they're the same.
So
Better hand off.
Really show us how we write this on the test.
Yep. Yep. Okay, so we'll come back to this. Okay, so in your calculator, this is what we did. Oops. This is the calculator notation, which is not acceptable for the test. This is how, for your notes purposes, this is how, if you have the old school version of the calculator, this is how you typed it in, 0 to 5. This is not acceptable for the test. What is acceptable is writing the integral notation, 0 to 5, e to the negative x squared dx is approximately, because that decimal went on, right? We can't say equals. You have to say approximately 0 point, and we do 4 decimal places here, right? 8862. All of that boxed up. You can't just say approximately 0.8862. You have to have the integral notation as approximately this.
That'll be accepted as long as it's a calculator.
If it's a calculator section, you have to show the setup, though. You have to show what you plugged into your calculator. Okay? Okay, I think there's one more down below. Would you try that one with your calculator? That'll be your last one.
Can I do it by hand?
Do you know how to do it by hand? Have you already learned how to do it by hand? Then no.
Try though.
Doing part B with your calculator. Now, that whole section is a binomial. I'd put all of that in parentheses. That's what I would always err on the side of adding extra parentheses, just in case. Make sure you do your lower bound first, then your upper bound last. Okay, now, are you getting it? This is what I've typed in. You have the old version. Type in your function, comma x, comma lower bound, comma upper bound. Now, here's where you might run into a problem. If we're taking this to 4 decimal places, how do we write our decimal? 876 point. You didn't get the same answer? Careful how you typed it in.
Is that close? But I'm 0.706.
Look at your mode. I'm in radians. Are you in radians?
I'm in no.
So since we have sine, change it to radians. Now do you get it?
Yeah, I got it.
Okay, so since there's a sine function, make sure you're in radians. Okay, but how do you cut it off? 0.79, you just leave it at 0.79 and cut it off?
Oh, you can?
No. You can't.
Oh, 0.901 because it's around the 7.
You can put it as, always it will be acceptable, 0.7901, and even 0.7900 is also acceptable because we can chunk our rounding. And they'll take either one of those.
So let's put 79.
If you put 0.79, it'll be wrong. If you leave it at 2 decimal places, it's wrong because it's not a terminating decimal right there. It keeps going.
So I have to show them the 2 zeros that I left out.
Uh-huh. So, again, calculator notation is different than what is acceptable on the test. We use, we used our f of x, comma x, comma 0.762, comma 5.314. But this is not acceptable for the test. Oh, bummer. Approximately 876.790000.
Homework next time, 15.
What?
15.
15.
We have questions on there, sorry.
Yeah, it's 6.2 questions next time, and the 6.1 is due next time.
So on the table, it's in units, and in the square column, it's in hours. You have to multiply everything by 60 to get it.
Okay, so the velocity is in meters per second, and then the